Today's lesson is about graphing quadratic equations. We're going to look at some ways of how to actually accurately graph the equation of a quadratic function. So these are kind of some steps, and this is certainly not the only way to do it, but this is one approach of how we're going to do it. Step one would be to find the axis of symmetry. If you remember from yesterday, we talked about the axis of symmetry being that line that cuts the parabola down the middle, so we know where it's going to be cut in half, which also tells us about the vertex, because we know the x from the axis of symmetry is also the x in the vertex, which gives us piece of the vertex. Then we just need to plug in that x value to find the y, and we have the actual ordered pair of where the parabola changes places. So put the vertex in the middle row of the table and fill in the table of values using your calculator. Okay, so you could do it with your calculator, you could do it by hand, you're certainly going to have to do some kind of calculation, and then plot the points and connect them into a smooth parabola. So let's check out our first example. So y equals x squared is the equation. We need to find the axis of symmetry. Now we remember the formula for that comes from negative b over 2 times a. And if we remember that the standard form for a quadratic equation is y equals ax squared plus bx plus c. So in this particular problem we only have one term, so we only have an a value here of 1. Since I don't have an x, I know that that was plus 0 times x. So this is going to be negative 0 over 2 times 1. So it's just going to equal 0. So our axis of symmetry is x equals 0. And we know that that x coordinate also matches the x coordinate in the vertex. So to find the corresponding y coordinate of the vertex, we simply plug in 0 to our equation to find out what y would equal. So y equals, when x is 0 squared, and 0 squared is also just 0, so the vertex of this particular equation, this function, is at 0, 0. So now that we have the vertex, we're going to make that our middle point, 0, 0, and we're going to try and find some points on either side. So we already know, we can already go ahead and put our point here, and we know that's our vertex, and it's going to come out symmetrical from here. So we usually try and pick some negative points and some positive points that are just kind of a mirror image of themselves. So if I wanted to start with some negative numbers, I would probably use like -2, -1, and then on the positive end, 1 and 2. You can certainly use other numbers, but since it's symmetrical, I really just need some good numbers going out both ways. You could have used some larger numbers to get a more accurate picture further out. These are the ones that I chose. So I can find the corresponding y value by plugging this x value into the equation, just like we do with the vertex. So for the first ordered pair, I'm going to erase some of this so we have some working room. I'm going to plug in -2 for x. So when I do that, I have y is equal to -2 squared. And -2 squared is just 4, so that's the y value for this one. Then we've got y is equal to -1 squared, which is just a positive 1. When I plug in the other two, I've got y equals a positive 1 squared, which is just a positive 1, and y equals a positive 2 squared, which is a positive 4. So once I have that middle piece, really, I truly only have to find a couple good points one way, and then it's going to be equidistant from that axis of symmetry the other way. So you don't have to do this method. Once you know the vertex, I could really find 4 negative points and then make them exactly the opposite the other way because it is symmetrical. So now we're just going to plot these ordered pairs. We've got -2, 1, 2, 3, 4, and then we've got -1, 1. It's going to be mirror image over here, 1, 1, and 2, 4. And now we just need to do our best to make it a smooth, curved parabola. It should curve and be symmetrical, and we're going to put our arrows at the end. So the next two blanks talk about domain and range. So just as a reminder, domain represents all the possible x values in the function, and range represents all the possible y values in the function. So since this is a graph that is connected, I know this is a continuous graph, and so we used to write the domain and range of continuous functions kind of like picture frames. We're looking at the boundaries. So when I'm looking at domain, I'm looking to say, what is the lowest possible x value here on my graph, and what is the highest possible x value here on the graph. So if you think about this parabola, it's going to continue going left forever, and we read the domain from left to right, from the negatives to the positives. So this is going to go into the negatives forever, so we would represent that with negative infinity, and it's going to keep going to the right forever, so positives forever, so it's going to go to positive infinity. So if you remember anything about domain and range, we had this whole concept of if a number is included on the function, it was notated with a bracket around it. So for example, if I had something like a line segment and it had endpoints that were closed at that number, say that was 2, we would have written it with a bracket and a 2 next to it. Well, we also learned that if a number was not included, so if it had an open endpoint at, say, 4, it would have a parentheses around it. So included numbers had brackets, not included numbers had parentheses, and something very important about infinity is that it can never get a bracket. It is a concept. It's not a number. It cannot be included. So whenever we do our domain or range and infinity is ever involved, it is going to start on the left side saying that it goes from negative infinity to positive infinity, and anytime infinity is involved, there must be a parentheses around it because it cannot be included. So looking at range, we did our range from the bottom to the top. So we were looking at what is the lowest possible y value now. So I'm thinking about this y-axis. What's the lowest it goes on here? Well, it actually does stop, and it stops at 0, and that is included. It's a shaded in point. Then we look at what is the highest part. Well, where we drew ours, it looks like it's stopping, but we've got to remember that there are arrows, and this thing's going to go up into the positive y values forever. So it's going to go into positive infinity. So we read it from the bottom to the top because that's how we read the y-axis. So the lowest point on our graph is definitely an endpoint here. It's going to stop at 0, which is included, so it gets a bracket. And this graph is going to go positive infinity as far as the y values are concerned, so it's going to go up to the positive numbers, and that always has to have a parentheses. So for domain, it's left to right. For range, it's bottom to top. So let's try another one. So example 2, walking through the process again, I'm going to find the axis of symmetry by doing negative b divided by 2a. Our b here is 2, our a is a positive 1, so we've got negative 2 over 2 times 1. So that's negative 2 over 2, which gives us negative 1. So the axis of symmetry, the line dividing the parabola, is going to happen at x is equal to negative 1. We know that is the x-coordinate of the vertex, so we're going to go ahead and put that there. And then we are going to plug in that x value to the function to find the corresponding y value. So I've got y equals negative 1 squared plus 2 times negative 1 minus 1. So negative 1 squared is a positive 1. 2 times negative 1 is a negative 1. And then there's a, it's a negative 2. And then there's a minus 1 at the end. So 1 minus 2 is a negative 1. And then minus another 1 is a negative 2. So if you couldn't keep all that straight, you could have just put this entire right side into your calculator and it would have done the order of operations for you. So the vertex here is happening at the point negative 1, negative 2. We're going to put that in the center point of our table. We're going to pick some other values to put above and below the vertex so that we can get a good spread. We'll use some bigger numbers this time to see if we can get some further out points and see exactly what it looks like. So this time I will use negative 4, negative 2, positive 2, positive 4. So remember, to get the y coordinates that correspond with these x values, we're going to just plug them into our function one at a time to get the corresponding y values. So I'm plugging in negative 4 first. So I would have y equals negative 4 squared plus 2 times negative 4 minus 1. So negative 4 squared plus 2 times negative 4 minus 1. So that's a positive 16 minus 8 minus 1. So that is an 8 minus 1. So that gives us 7. So then we're going to do it again with negative 2. So we've got negative 2 squared plus 2 times negative 1 minus 1. So that's a positive 4 minus 2 minus 1. So 4 minus 2 is 2, minus 1 is going to give us 1. So truly, this should match. It should go back up like a mirror image. It's going down, there's the changing point, and it starts going back up. This should be 1 and this should be 7. We can plug them in just to check. So if I plug in a positive 2, I will have 2 squared plus 2 times 2 minus 1. So that would give me 4 plus 4 minus 1. So that should be 8 minus 1, which is 7. Okay, so because this is not directly in the middle, it is not going to come out from this middle part. It's really going to come out from the axis of symmetry, which this time is shift over a little bit. So it's not going to go down and then back up. So good thing we checked, because I definitely misspoke. Alright, so when we plug in a 2, that comes out to give us 4 plus 4 is 8, minus 1 gives us a positive 7. And then when we plug in a 4, we've got a positive 4 squared plus 2 times 4 minus 1. So that is 16 plus 8 minus 1. So that would be 24 minus 1. So that should be 23. So this one's going to go off our graph a little bit. So we really can only plot the first few. So we've got negative 4 and then 7. 1, 2, 3, 4, 5, 6, 7. Negative 2, negative 1. We know our vertex was negative 1, negative 2, so this should be the turning point. Then we've got 2, 7, so 1, 2, 3, 4, 5, 6, 7. And then our next one should be 423, which is way up there. Okay, so if you wanted to fill in the gaps, you could plug in some other points. So say I wanted to know what 1 is going to be, so I could plug in a 1 to find out where I could accurately put one of these points. So say I plug in 1 for x. To figure that out, I'd have 1 squared plus 2 times 1 minus 1. So that's 1 plus 2 minus 1. So that's 3 minus 1, so that would give us 2. So we've got 1, 2. And if you wanted some more points in here, you could plug in a negative 3 to find out where it's going to fall in here. So plugging in a negative 3 would give you that point. Also, you could think of this axis of symmetry, and it has to be equidistant from this axis of symmetry. So if at this point it's 2 to the right, it has to be 2 to the left over here. So a lot of teachers will just have you find the axis of symmetry and maybe 2 or 3 good points on one side and then reflect it over the axis of symmetry. So for example here, since I know I have a point one way to the left, I'll have a point one way to the right. So you will connect these, try and make it as much of a curved equal symmetrical parabola as possible. Put your arrows on the end. We've got to do our domain and our range. So again, our domain is the boundaries on x, and unless a parabola is not a function, like at any time a parabola faces up or down, your domain's always going to be the same. It's always going left forever and right forever, left forever and right forever. It's only if the parabola is not a function, if it's turned sideways, which is not a function, then the domain would change. But for all these quadratic functions, the domain is always going to be going left forever to right forever, so it's going to be from negative to positive infinity. Now your range is what's going to change depending on if it's facing up or facing down. So our range is the lowest value on y, which it looks like a negative 2 here, to the highest value on y, which it's going up forever, so that's positive infinity. Negative 2 is included part of the graph, so that's going to be from negative 2 to infinity. So a lot of students will start noticing, based upon the front number here, whether or not it's positive or negative, whether or not the parabola is going to open up or down. If the parabola is opening up, you're going to have a minimum value, which is where your range is going to start, and it's going to go up to positive infinity. If your number out front was negative, this thing would be facing down, and it would start with negative infinity and go up to that number. So we're going to see one like that here in just a few moments. So number 3 is one that could be that way. So before I even do any of this work, I know that this is going to be facing down because of the negative a value. So I have negative b over 2a. So our b here is negative 8. So we got negative 8 over 2 times negative 1. So a negative 8 is a positive 8. 2 times negative 1 is a negative 2. So our axis of symmetry is going to happen at x equals negative 4. So we can really go to negative 4, 1, 2, 3, 4, and this is where our parabola is going to be cut in half. So now I'm going to start using this axis of symmetry to make better judgments about which points to choose to plug in and get a clear picture of the parabola. Alright, so that x value becomes part of our vertex. We need to plug in that x value to the function to find out the corresponding y value of the vertex. So we've got negative 4 squared minus 8 times negative 4 minus 17. So being very careful with all these negatives. I've got negative 4 squared would be a positive 16, but there's a negative outside, so it becomes negative 16. Negative 8 times negative 4 is a positive 32, and then I have a minus 17 at the end. So negative 16 plus 32, that gives us a positive 16, and then 16 minus 17 is going to leave us with a negative 1. So we're going to put that in the middle, negative 4, negative 1, and we know negative 4, negative 1, this is where our vertex is going to be, right there on that axis of symmetry. So now, to be wiser about where I'm going to pick some points, I'm going to want to pick maybe 2 to the left and 2 to the right of this axis of symmetry. So I might want to use negative 5 and negative 6, or I could use negative 7. So I'll choose negative 5 and negative 6. And then 2 points to the right here, negative 3 and negative 2, to get a clear picture of what's going on. So when we plug these values into the function to get our corresponding y coordinates, we will be able to accurately graph the function. So before we do that, I want to prove to you that I can figure out the domain and range before even knowing all of that. Well, I know that this parabola is going to face down. I know that much at least. So I know it's going to have a maximum value. I know that if I'm reading the domain, it's going to go left forever and right forever, so that's still going to be from negative to positive infinity. The thing that's going to change is going to be our range. So our range, the lowest value on y is going to be the fact that it's going down forever. So it's actually going to start at negative infinity because the range is going down forever first. There's going to be a maximum value, and that value is going to be the y value in the vertex, because this is the point, negative 4, negative 1, where it stops. So I know this maximum y value is going to be that y value from my vertex. So I already know that my range is from negative infinity up to negative 1, and that's going to be included, so it gets a bracket. So let's finish this, show our drawing, and I'll prove it to you, but you can actually see that before you have your graph. So when we plug in all these values, we've got negative 6 squared minus 8 times negative 6 minus 17. So negative 6 squared would become a positive 36. Then there's a negative outside, so I got negative 36 plus 6 times 8, which is 48, and then minus 17. So when I do these calculations, a negative 36 plus 48 minus 17 gives us a negative 5. I'm going to do it again with a negative 5. So we've got negative 5 squared minus 8 times negative 5 minus 17. So that gives us 25, but there's a negative out there, so it's negative 25 plus 8 times 5 is 40, minus 17 when I do those calculations. Negative 25 plus 40 minus 17 gives us a negative 2. We'll do the other two, and then from here we'll talk about what else you could do aside from this long process. So we've got negative 3 squared minus 8 times negative 3 minus 17. So that's 9 squared. The negative outside, comes 9. There's a negative outside, plus 24 minus 17. So negative 9 plus 24 minus 17 also gives us a negative 2. And then if we equidistance these correctly, this should be going back up because we use this axis of symmetry and went from both sides. So when I plug in negative 2, it should give me negative 5. Let's check it out and see if that's the case. So we've got negative 2 squared minus 8 times negative 2 minus 17. So that's positive 4 with the negative outside, and that's plus 16 minus 17. So negative 4 plus 16 is 12, minus 17 is negative 5. So we did a good job of picking points this time, and it should go straight out from there. So we've got negative 6, negative 5, 1, 2, 3, 4, 5, negative 5, negative 2, negative 3, negative 2, negative 2, negative 5, and then we just do as best a job we can of making this curved and symmetrical. And then so just like I said, our domain from the left to the right, it's going to keep going left, down forever, forever, right, forever, forever. So it's going on the x values, negative x values forever, positive x values forever, which is negative to positive infinity. Then for range, we looked at the bottom y value, which there is no bottom y value because it keeps going down forever. So that is called negative infinity. And then at the top, there is an actual y value where it stops, and that is at the y value negative 1. It's included, so it gets a bracket. So now you should know how to do it by hand if you didn't really have a graphing calculator. You could do all of that. In the event that you are actually allowed to use your calculator, you can actually plug these in and look at the table on your calculator. We'll talk more about that in class. If you can figure it out, you're just really going to go to the y equals function on your calculator, and you're going to plug in the right side of the equation. You're going to just type that into your calculator. So for here, and if I had my little y equals all in the calculator, then I would type in the right side into the calculator. And then once you have that in there, you can actually look at the table. It is on one of the top buttons right underneath your screen. You can hit table, and it gives you a table of values. So we're going to talk about an easier way, but I do want you to know how to do it by hand. All right, so for the rest of tonight's homework, what I want you to try is numbers 4, 5, and 6 on your own. We'll talk about them, and then we'll determine whether or not we're going to do any more in class. Because you're doing these mostly by hand, I'm only giving you 3. We'll try those 3. If you feel like you need more practice, you are certainly welcome to go all the way to, I think there's like number 11. You're certainly welcome to go that far, but just for the idea of getting practice, I want you to do the next 3, bring them in with you with your notes.